We've seen how, at least in principle, we can take a program which is checking proposed solutions to a problem in NP, like checking proposed tours through a graph, proposed Hamiltonian tours, that at least in principle we could compile it, transform it all the way down into a Boolean circuit. We've seen how to translate Boolean circuits in turn into logical formulas, which are satisfiable, which can be made true by some setting of their variables, if and only if that thing, the Hamiltonian path or whatever, exists. What we've actually done is we've proved that 3-SAT, which is one of the original 6 NP-complete problems defined and studied by Cook and Karp, is NP-complete. So here's 3-SAT. You've kind of already seen it. An example or an instance of 3-SAT is a logical formula. It's the and, remember that upside down V, of a bunch of clauses, each one of which is an or of 3 things. Each one of those is a variable or the flipped negated version of that variable. So for instance, this formula demands that either x1 is true, or x2 is false, or x3 is true. And it also wants it to be the case that x2 is true, or x17 is true, or x23 is false. And it wants a bunch of other things too. And the question, the decision problem, the yes or no question is there a way to set these variables, flip all these switches, so that the entire formula is happy and satisfied? Incidentally, we saw before that sometimes we want to think about clauses with 1 or 2 variables instead of 3. It's not too hard to pad things up so that they all have exactly 3. Okay. Now, we call this 3-SAT because there's 3 variables per clause. K-SAT is k variables per clause. And in fact, K-SAT is NP-complete whenever k is bigger than 3. At the risk of beating a dead horse, let me remind you what's going on here. If 3-SAT were easy, we could take any problem in NP we want to solve, write a program that checks solutions, convert that program into a circuit, convert that circuit into a 3-SAT formula, which is satisfiable if and only if a solution exists. You say 3-SAT's easy, I don't believe you. You say it's easy, you run your fantastic algorithm on it, and you give me the correct yes or no answer. So if 3-SAT can be solved in polynomial time, then all of NP can be solved in polynomial time, and P and NP are the same. And if they're not, if there is any problem in the world where finding is hard but checking is easy, then 3-SAT can't be solved in polynomial time. It must require some kind of exhaustive search. And let me point out that if I have n variables, x1, x2, up to xn, if each one can be true or false, I have 2 to the n possible solutions, an exponential haystack of possible solutions in which we're trying to find our needles. We're going to get away from these Boolean problems fairly soon, but I just want to give 1 or 2 more examples of how these reductions work. In particular, I can take K-SAT for any value of k, clauses that include the or of combinations of k variables, and I can break them down into 3-SAT clauses. In other words, 3-SAT is a powerful enough building block to build up clauses of any length, which is partly why 3-SAT is hard. How does this work? Well, when I transform from an example of K-SAT to an example of 3-SAT, I'm allowed to invent additional variables if I want. So here I have x1 or x2 or x3 or x4 or x5. This is a 5-SAT clause. It wants at least one of these 5 things to be true. I can invent new variables, I'll call them z1 and z2, and I can use them to break this 5-SAT clause into 3-SAT clauses, and then use them as glue or staples to connect it all together. I'm going to leave this for you as an exercise to check that it works. But in fact, if you play with it, you'll see that there's no way to set these variables, including z1 and z2, so that all 3 of these things are true unless at least one of those 5 variables are true, and vice versa. So 3-SAT, again, it's a powerful building block. You can go to the hardware store, buy a couple dozen 3-SAT clauses, and build all kinds of logical relationships. Interestingly enough, 2-SAT clauses aren't. If you have, let's say you go to the hardware store, they're out of 3-SAT clauses, all they have is 2-SAT clauses. Little things that just say things like, X is true or Y is true, or X is true or Z is false, only 2 variables at a time. These building blocks just aren't good enough to build more complicated logical relationships. One way I like to think of this is that 3-SAT allows some chemistry. So for instance, when I say that X or Y or Z is true, it means that if X and Y are both false, Z must be true. It's like a chemical reaction with 2 things going in and a product coming out. 3-SAT is also powerful enough to make choices in a sense. Again, if X and Y and Z, if at least one of those must be true, if X is false, then Y or Z must be true, but it could be either one. This gives 3-SAT the ability to make choices and thus, in some sense, search among a variety of possible solutions. Whereas 2-SAT, well, if X or Y, if one of those must be true, big deal. If X is false, Y is true. It's just a kind of single arrow with one thing going in and one thing coming out. And this is maybe a bit too challenging to throw at you, but if you feel up to it, try to prove that 2-SAT is in fact in P. All you really need to do, okay, here's a hint, is follow these arrows around the formula and see if there's a loop which creates a contradiction. If assuming X is false causes something else to be true, which causes something else to be false, which blah, 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 circles back to setting X true, but that causes some other chain reaction, which circles back to cause X to be false again, well, then you have a contradiction. And the formula is not satisfiable. So 3-SAT is NP complete, 2-SAT is NP.